All right, today our topic is domain and range. So first I'm looking at this solution region, right, that's graphed on a number line, and I want to express that in two types of notation. So first is the inequality notation. We focus on this a lot in Algebra 1. So here I would think of this as whatever variable you like. Usually we start with x, and we say that x is greater than, it's more than, or equal to, because it is filled in right here. So greater than or equal to 5. Okay, and as you move up in math, we like to switch to interval notation, where we use the bookends. So when I think of over here in the number line, this is negative infinity, and over here this is positive infinity. So if I'm looking at the bookends of what my possibilities are, my value x can be anything from 5 to positive infinity. So we're looking at the two bookends from 5 to positive infinity. So we'd say from 5 to positive infinity. Now, since it's filled in here, it can be equal to 5. We use a hard bracket to show when it can be equal to that value. But infinity is an idea. It's the biggest number we can possibly conceive of. So we're never exactly equal to infinity. That takes a soft parenthesis just like that. So this reads as any value from 5 to infinity. It can be equal to 5, but not to infinity. Okay, over here, if I write this first in inequality notation, I know that I'm looking at anything that's between -7 and 4, but can't be equal to -7. So first I start by putting my variable right in the middle. There's x. X has to be greater than -7, right, but not equal to, so I'm not giving a dash here. And at the same time has to be less than 4. So you can see that my arrows are the same direction. So less than or equal to 4, right? Because it's solid right here. It's filled in. So it takes a little dash right here. And then there's my 4. So here we're saying that x is both greater than -7 and at the same time less than or equal to positive 4. So that little dash means it can be equal to that number. Okay, and if I switch to my interval notation, right, we know that it's going to be between -7 and positive 4. It cannot be equal to -7, so that takes a soft parenthesis right there, but it can be equal to 4, so that takes a hard bracket just like that. Okay, so next up, we're looking at domain versus range. So domain is the spread of possible x values. So we think of it as the minimum x to the maximum x value. And the range is the spread of possible y values. So we think of it as the minimum y value to the maximum y value. So here I'm saying, well, let's return to something familiar. Let's go back to parent functions. And then I'm saying state the domain and range afterwards in interval notation. All right, so the first function that we see, f of x, is equal to x squared. This is quadratic. So we should know the name of it, and we should also know what it's going to look like. So a quadratic is a parabola. It's that beautiful U shape. And hopefully you actually know what your points are as well for your parent. So a little refresher here. I'm making a little table. So my inputs are going to be -2, -1, 0, 1, and 2. And when I plug back into my function, I'm picturing plugging back into parentheses and squaring it. So -2 as a quantity squared outputs as 4. -1 as a quantity squared in parentheses ends up outputting as 1. 0 is 0. 1 is 1. 2 ends up outputting 4, right? 2 squared gets us 4. So when we graph it, we start with the vertex right there at the origin at 0, 0. And then from here, we go over 1 and up 1 in both directions. So here and here. back to the origin. That's our anchor position. Now we go over 2 and up 4. So here to here. If I wanted more points, I could go back to my origin, go over 3, up 9, right? But it's not necessary. So here's my quadratic function, right? A beautiful parabola, this U-shaped graph. And then my domain. If I think about it, right, I'm reading left to right because I'm looking at my x values. It keeps growing to the left, it keeps growing to the right. I can also think about when I look at the equation, what can I plug in for x? And I can really plug in anything for x. So my domain could be all real numbers. I could express it like that. Or I could say from this extreme to this extreme, which is negative infinity to positive infinity, which always takes parentheses. We're never quite equal to either of the infinities. We're just picturing it as the smallest number we can conceive of, the biggest number that we can conceive of. All right, for range of it, the y value, so my y values start off really big, come down, hit this minimum value of 0, and then they get big again, right? I have all of this empty space down in this negative territory for y. So my y values are always greater than or equal to 0. But again, I want interval notation. So we're saying from 0 to positive infinity, hard bracket on the 0 because it has a value at 0, never on infinity. Okay. Next function over here. This is our square root function. When I visualize it, I think my anchor position at the origin, and this little curve off to the right, that's what it looks like. So again, if I make a little chart of inputs and outputs, when we input for the square root function, we like to use perfect squares. So 0, 1, 4, 9. The reason we like perfect squares is because when we take the square root, it gives us a nice clean integer value. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So I start by putting my anchor position at the origin, and then over 1, up 1, back to the origin, over 4 and up 2, back to the origin, over 9 and up 3. And then smooth out the curve just like that. Okay, my domain, I don't have any values over here that are below 0, so I know that x has to be greater than or equal to 0, but we'd say from 0 to infinity. It does have a value at 0, never infinity. Okay, for the range, again, we have no value for y that's below 0, so we know that the y has to be greater than or equal to 0. But if I put that in interval notation, right, again, our lowest value is 0, and then it keeps growing up, keeps getting bigger, so 0 to infinity again. Hard bracket on the 0, never on infinity. So just a reminder also that when we're looking at domain, we're always reading our graph from left to right, all of the possible x values. And for the range, we're reading it from bottom up, right? The minimum y to the maximum y. All right, next up. All right, so here we're looking at absolute value. So absolute value, let's name it first. Okay, when we see that, we think, okay, it's going to be this lovely V shape. It's like two lines that meet at the origin that have different slopes. One has a slope of 1, the other one is -1, and again, they meet at the origin. If again, I picture this table of inputs and outputs, let's say that I input a -2, -1, 0, 1, 2. Whenever we input into absolute value bars, the bars force it to be a positive. So if I put in a -2 into absolute value, it becomes +2. -1, when I put it into absolute value bars, becomes +1. And then 0, 1, 2. All right, so plot a point at the origin. And then from the origin, we go over 1, up 1, both directions. Back to the origin, over 2, up 2, right? And that pattern would really continue. Over 3, up 3, over 4, up 4 in both directions. So makes this perfect V that is really a line here with a slope of +1 and a line here with the slope of -1. All right, when we picture the domain, what can X be? We know that it's going to keep growing from left to right. If we think about it just from the equation of it, we can really input anything in for X. So we could say all real numbers or negative to positive infinity, and that's our interval notation. Okay, for our range for Y values, they start off really big, they get smaller till they hit that minimum value right there at the vertex, and then they get bigger again. So for Y, right, there's no value here in the negatives, so Y has to be greater than or equal to 0, or 0 to infinity, hard bracket on the 0, never on infinity. All right, one more graph. So here we're giving you 2 to the x power. So anytime we see a variable in the exponent position, like so, when we have x in that exponent position, this is an exponential function. Okay, but that base value doesn't always have to be 2. This is just what we start off with. We start with a base of 2, but really we can change it. We can make it 10. We can make it 1/2, right? It can really be anything, just not 0 or 1. So here when I picture this, I'm picturing an asymptote. Okay, and then I'm picturing my curve that goes like this. That's my visual for an exponential function. So again, if I make a little table to start, inputs and outputs, I'm going to use -2 up to +2. And when I input, I'm saying 2 to the -2nd, 2 to the -1st, 2 to the 0, 2 to the 1, 2 to the 1st, 2 to the 2nd power, like that. So if I'm saying 2 to the -2nd power, that's like saying 1 over 2 squared. So that's 1/4. 2 to the -1st, that's 1 over 2 to the 1st, so 1/2. 2 to the 0 power is 1. 2 to the 1st power is 2. 2 to the 2nd power is 4. So if you look at these Y values, you should be able to see that they are doubling from stage to stage, and that's because the base is 2. If my base was 3 instead, they would be tripling from stage to stage. All right, so now when I plot my points, I'm at -2. Here I'm up 1/4, and then 1/2, and then 1, and then 2, and then 4. And if I kept doubling, my next one would be up 8, right there. Okay, now I said that we have an asymptote for this function. So if you think about this conceptually, imagine that we picked a number that's way deep over here in negative territory. Let's say I picked something like -20. That would be like saying 2 to the -20th power, which is 1 over 2 to the 20th power, which I may not know exactly what that is, but I know that that's taking 1 and dividing it by something that is really, really big. So overall, that's a number that's going to be really tiny. It's going to be really close to 0, but never exactly 0. So no matter what I input in for x, it's going to always output something positive. And if I'm picking something for x that's negative, way deep over here, I'm just picking something that's going to be closer and closer to 0, but never exactly 0. So I end up with this horizontal asymptote here at y equals 0. Okay, and then I smooth out my curve like so. There's my exponential function with a base of 2. Now, my domain, right, I could input anything for x into this function, right, whether I'm way over here deep negative or over here deep positive. So all real numbers, right, it's going to keep growing if I think of it left to right, or negative to positive infinity. But no matter what I plug in for x, it's always going to output something for y that is more than 0. Right? It's always going to give me something that is positive, whether over here it's a y value that's really tiny, or over here a y value that's really big. It's always going to be more than 0. So in interval notation, that's 0 to infinity, soft parenthesis, on the 0, always on infinity. All right, have a good day.